So this video is picking up from where we left off before, where we were drawing force one, where this is about 2 newtons worth of centimeters, which you can look at the measurements from the previous video at 30 degrees above the horizontal. We made a new coordinate system using this because we know that these are alternate interior angles. This horizontal line must be parallel to this. So if this is 30 degrees. So using that, we drew this new one, which is supposed to be F2, added head to tail to F1. The reason why we're doing this is because we want to see the total effect of the ring, of the forces of F1 and F2 on the ring. So we have to draw these all to scale, where this angle here now, oops, not this color, I wanted to make it black, where this angle here is going to be 70 degrees. And this magnitude here, right, the length of it that you're drawing on your paper is going to be equal to 6.867 centimeters, right? And this is the vector head. So what this is telling us is instead of thinking of your ring being pulled on by these two forces at these two different directions, you can instead think of it as one single force with this magnitude in this direction, right? That's what a resultant is. It's the sum of the two other ones. So F1 and F2 make up this one neon colored one, right? And so we want to find how much this force is, right? We want to see the total effect of those two forces on the ring. And so we take out a ruler, we physically measure it, and let's say we get um, like 9, let's say we get 10 centimeters, right? We measure it out and we get this entire length is 10 centimeters. 10 centimeters, right? And so if it's 10 centimeters, we want to see how much force that is. So if this is 10 centimeters, we want to find how many newtons it is. So that would be about 5 newtons, right? 10 centimeters, if 1 centimeter is half a newton, 10 centimeters would be about 5 newtons. So on here, on our accepted values, we get 10 newtons, right? This is based on our scale diagram. For the direction, we want to physically measure it. So take out your protractor and you measure out this total angle for the horizontal, right? And that angle is going to be your resultant. So this total force, and actually this is kind of skipping ahead, your F total, right? F total is equal to 5 newtons at, and let's say you measure this and you get 55 degrees. Right? Let's say you have 55 degrees. So this is saying that instead of thinking of it as F1 and F2 acting on the ring, you have one force of 5 newtons that's directed 55 degrees up for the horizontal acting on it. That's it. So our third force for your first task was to was supposed to balance all this out. Now we talked about equilibrium forces in class, right? Where you just take the total and your equilibrium force is the same thing as this magnitude, 5 newtons worth of force, but exactly opposite of that direction. And it kind of makes sense, right? If you have one force directed to the right, that's 10 newtons. How do you combat that? How do you make it all balanced? You have a 10 Newton force directed exactly opposite of it, right? Same magnitude, but opposite in direction. And this is the centerpiece. Like this is where the tails of the arrows align, where this is 10 Newtons. And they completely balance out, right? So equal and opposite of your total force. So if this is our total force, equal and opposite means equal magnitude, 5 Newtons, and direction exactly opposite from 55 degrees. If 55 degrees is here, exactly opposite that would be this way. So you're adding 180 degrees to it, right? Exactly this would be 180 degrees away from it. So 180 plus 55 gives you 235. So your equilibrium force ideally should be 235 degrees away, right? So now you do percent error. This is what you got experimentally, and this is what we got based on our drawing. So percent error, the equation for that again is, and we have it in our board. I want to see if I can type it somewhere. So it's equal to your equal equation. Absolute value percent error is equal to absolute value of a fraction, accepted value minus experimental value, all divided by your accepted value. Let's make this font a little small so we can fit it all. Multiply by 100%. This is your equation for accepted value for percent error, right? So we've done this before when we typed it into our Google Sheets. So it's equal to absolute value ABS of, I'll put another parentheses there. For this is for your magnitude. So I'm going to take my accepted value, which is this, subtracted by what I got on my experiment, close parentheses, divided by my accepted value, all multiplied by 100%, 3.862, right? And so for my angle equals, again, same thing, right? Absolute value of 235. Actually, I want to put another parentheses. 235 minus 235 divided by my accepted value, close parentheses, multiplied by 100%, and 0% error for this. So these are my percent errors. Right now, there is some percent error for my force, but 4%, 3.862% is really not a lot, right? So it's pretty good data. For direction, 0 degrees, 0% error, which is perfect data, right? So make sure when you're writing your data interpretation, you explain maybe what factors into having a percent error, right? Why did my data not come out perfectly? We didn't expect it to come out perfectly, but we have to try to understand why that happened. So this is your analysis for part one by using vector addition. Okay, so again, just to make sure we all understand this, even though I did this digitally, for your lab, you need to draw this out and take a picture of it and copy and paste it into your lab report. So a scale diagram is required for your data presentation. Okay, and if you want to include this template for your data, that's fine. Right? Hope you guys have a good weekend, and I'll see you guys on Monday.